In this video, I will go over a paper that Chelsea Finn and I presented at the NIPS 2016 workshop on deep reinforcement learning, and I'll use our poster here as a reference. So the problem we were addressing was online active learning. And in online active learning, the system is processing a stream of data points, and it needs to decide on each time step if it would like to get the label for the current data point, or if it can just go ahead and predict from the information it already has. Okay, and there are two main contributions of our paper. The first was we framed it as a reinforcement learning problem, which we believe makes for a more principled approach to making that decision of whether you want a label or not. And the second is we trained in a meta-learning style training, which allows for rapid learning. So the system can learn from as few as 1 to 2 class examples. Okay, so the poster here. So the data points we used, or the problem we are actually addressing in the paper, was online image classification. So the data points are a set of images, and the data set we used is this Omniglot data set. And the Omniglot data set is made up of 1,600 classes, so 1,600 characters from different alphabets around the world, and each character has 20 hand-drawn examples in it. Okay, so the agent will be getting, several of these, or getting these examples of these, and it will need to decide whether it wants a label or not, wants to get the label for it. Okay, and so more specifically here, the agent can choose to request a label, and it does that by outputting a 1. So the outputs of the agent are a 1-hot vector, and the last element of that says I would like the label for this image. So if you set the last bit of that, you'd like the image on the next time step, or you like the label for the current image on the next time step. And you incur a reward of minus 0.05, which we've set here, for requesting that label. So you request the label, and then on the next time step, you get in the image, which is the xt of the next time step, but you also get in this label of the current time step that you requested. But if you're going to predict, then you just set one of the first n bits of that vector to be the class that you believe that current example to be. And then on the next time step, you don't get a label because you didn't pay for it. And then the agent incurs a cost, so +1, or a reward +1 for correctly labeling, and -1 for being wrong. Okay, and since it's a reinforcement learning problem, we modeled this or we used Q-learning for this, and for the Q function, we approximated that with an LSTM. And the inputs to the LSTM, so it's just a single layer LSTM, 200 hidden units. The inputs to the LSTM are a 1-hot vector of the labels from the previous time step if you requested them. That could be all zeros if you didn't request them. And that's concatenated with the flattened vector of the image for the current time step. And that goes right into the LSTM, and then there's a linear layer on the output of the LSTM that draws it down to the dimension of the actions, which is sort of the number of classes +1. +1. Okay. And then you can just take the maximum of the LSTM outputs to make your decision of which action to actually take, prediction or requesting a label. Okay, now to look at some results. So, first I mentioned that we trained in a meta-learning style. So the way that happens is we train on episodes, just short episodes of about 30 time steps. And so that'll be 30 images, and they're drawn from a small subset of, about 3 to 5, well, 3 in this example, classes from the Omniglot data set. So 3 of them are randomly chosen, and then 30 examples are drawn from those 3 classes, and then that constitutes, and they're randomly ordered, and that constitutes the episode. And then the labels for those are randomly permuted too, so no episode has sort of the same labeling. And what this sort of training method does is it forces the weights of the network to sort of learn about learning, and they can't, because you're constantly changing things in each episode, they can't memorize the data set. I mean, with enough runs, it may be able to, but it certainly couldn't memorize the labels. And then we'll see in the results that it actually doesn't seem to be memorizing the actual examples too, because it works fine on classes that it has not seen before. Oh yeah, actually you can see that in the paper for more references. Okay, so within an episode, there's going to be a first instance of a class, a second instance of a class, a fifth, and a 10th. And for each of those instances, so what we've plot here is how many. So for the first instances of the classes that are in that episode, we saw how many of those, or what percentage of those, did we request labels on, and did the same for the second, fifth, and 10th. And then the x-axis here is the training episode. And then at the 100,000th point, we stop training, we switch over to the test set. So this is performance on the test set out here. So if we can look at that on the first instance, we're requesting a lot of labels, and then on the second, it drops dramatically, and the requests are way down. So you often request on the first instance of a class, and much more rarely on the second instance of the class, which is what we want to see in rapid learning. And then same for accuracy here. It's not very accurate on the first instance of a class, but then it rapidly on the second, fifth, and 10th becomes more accurate. And that's that. Okay, and then just point out one more thing here. I said this is sort of a more principled method of deciding when to request a label. So the way that's currently done, or was previously done in active learning, was you would either look at the uncertainty of the prediction and set some threshold and decide whether to request if uncertainty in your prediction is pretty high, but it's unclear how to set that threshold. Another way is to look at how much your classifier is going to change. So maybe the weights of your classifier, depending on which label you received for that example, they might change a lot or little. And if they change a lot, then maybe I would like to actually see that label. But both of those are sort of heuristics. It's kind of difficult to set what the threshold would be there. But in this setup, we're just the only things we're specifying are these three labels. So what it costs you to request a label, and then what it costs you to be right and wrong, if the system were right and wrong. And that's, in our opinion, a little more principled, or easier certainly to set. So these are numbers that a hospital might actually know. So they might know how costly it would be to misclassify an X-ray. And they would also know how costly it is to actually query a doctor for that X-ray. So those are sort of numbers that maybe more easily set than more arbitrary thresholds on uncertainty. Okay, and so this little table here, we varied the cost of being wrong, and just watched what happened to the accuracy in the requests. And so this we can look at this third row here. You can see the details in the paper, but this third one is this the reward for being incorrect is -1. That's what we had up here and in all those experiments. Okay, so that was -1, and we started with an 81% accuracy, and then as we started to make it more costly to be wrong, the accuracy on the ones that we actually do predict keeps going up, which is what you'd like to see. But at the same time, so does the number of requests you actually make. That goes up too. This 60% isn't really. This is over only 30 time steps. So you can imagine, the system would be up and running, and it would run for thousands of time steps, and classify thousands of images. And so this is your requests over the very first 30 of those time steps. Okay, so that's pretty much it. You can see the rest, the paper for the rest of the details. Yeah, basically, so we showed that, online active one-shot learning is possible. So that means that we can learn rapidly from very few examples. And then also there's sort of, and goes with that principled approach I said for making that decision, that by setting the rewards, the system dynamically changes how willing it is to make a request versus prediction. So that's that. Thank you.